Now that we have a basic understanding of how interrupts are typically handled, let's look at the relationship between interrupts and threads. Recall from the previous example that when an interrupt occurred, there was a possibility of a deadlock. And this was happening because the interrupt handling routine was waiting on something, was trying to lock a mutex that was already held by the thread that was interrupted by that interrupt routine. A similar situation could have happened for the signal handling routine. So how can we solve this? One way that's illustrated in the SunOS paper is to allow interrupts to become full-fledged threads, and that this should be happening every time they're potentially performing blocking operations. In this case, although the interrupt handler is blocked at this particular point, it has its own context, its own stack, and therefore it can remain blocked. So at that point, the thread scheduler can schedule the original thread back on the CPU, and that one will continue executing. Eventually, the original thread will unlock the mutex, and at that point, the thread that corresponds to the interrupt handling routine will be free to actually execute. The way this happens looks as follows. Whenever an interrupt or a signal occurs, it interrupts the execution of a thread. And by default, that handling routine should start executing in the context of the interrupted thread using its stack and its registers. If the handling routine is going to be performing synchronization operations, in that case, that handler code will execute in the context of a separate thread. When the locking operation is reached, if it turns out that this one blocks, then the handler code and its thread will be placed on a wait queue associated with the mutex, and instead the original thread will be scheduled. When the unlock operation happens, we go back and we unschedule, we dequeue the handler code from the queue that's associated with the mutex, and the handling routine can complete. This sounds like it makes sense. However, one concern is that the dynamic thread creation is expensive. The decision that needs to be made dynamically is whether or not the handler should be handled on the stack of the interrupted thread or as a real thread. The rule that's described in the SunOS paper that's used in the Solaris system is that if the handler routine doesn't include locks, then it's definitely not going to block, and so it's safe to execute it on the stack of the interrupted thread. However, if there is a possibility for the handler to block because it tries to lock mutexes, then we turn it into a real thread. In order to eliminate the need to dynamically create threads whenever it's determined that a handler can potentially lock, the kernel pre-creates and pre-initializes a number of threads for the various interrupt routines that it can support. What this means is that the kernel will pre-create a number of threads and their associated thread data structures. It will initialize those data structures so that they point to the appropriate place in the interrupt handling routine, so that any interrupt internal data is appropriately allocated, and similar types of activities. As a result, the creation of a thread is removed from the fast path of the interrupt processing. So we don't pay that cost when an interrupt actually occurs, and therefore the interrupt handling time can be significantly sped up.